Up to this point, we're pretty familiar with how to graph polar curves, but in this video, let's talk for a little bit about how you find the area of polar regions. So as you're sketching these polar graphs, sometimes you make very natural regions that are either enclosed, or you want to find, even if it's not enclosed, you want to find the area in a certain portion of a polar graph. Let's discuss, how we might do that. So here's a couple of very typical polar graphs. Here we have a rose curve, and here we have what's called a limacon. A limacon has this thing called an inner loop right here, and these are just two typical polar graphs. There are others. I just arbitrarily picked these guys. And so examples of areas of polar regions that we might want to find might be maybe an area of one of the petals of a rose curve, or maybe the area of just the inner loop of a limacon, or maybe even all the petals of a rose curve or something like that. So these are very typical questions that we see from time to time. And it turns out there's just a formula that we use to get this area. Now, as you well know, just being in a calculus class, when you're talking about area, you're probably talking about an integral, and that's true here as well. So the definition is a little wordy, or the theorem is a little wordy, so let's read it and then I'll break it down for you. All right, let's let r equal a function of theta, as it typically is. This makes a polar graph. And there's a condition on this guy. It does have to be non-negative. If you have negative, like positive and negative r values, and you try to do this theorem here, try to use this formula, it doesn't work. So the r values always have to be in front of you, none of those negative r values that are graphed behind you. Now that might worry us a little bit with something like a rose curve. If you remember these examples, some of these petals are drawn with negative r values. We'll talk about those in just a minute. Okay. All right. Non-negative on an interval of theta. So theta starts at an alpha and it ends at a beta. So like 0 to pi over 2, or negative pi over 6 to pi over 6, or some range like that, where we have this other weird stipulation. 0 is less than beta minus alpha minus 2 pi, or I'm sorry, less than or equal to 2 pi. 0 less than beta minus alpha less than or equal to 2 pi. So what does this mean? Well, this is just a shorthand way of saying b cannot be any more than 2 pi units ahead of alpha. On the one hand, it says that beta has to be bigger than alpha. If that difference has to be positive, beta has to be the bigger one, but it can't be much bigger. So like if your alpha's here, your beta can't be around and around and around and around in here, right? So that when you subtracted those angles, you can't have a difference greater than 2 pi. Okay, but usually that's not the case. Usually your angles are, fairly close to one another, certainly no more than 360 degrees ahead of the other one. Right, if that's the case, then the area bounded by that region and what we call these radial lines. A radial line are these straight lines at alpha and beta, right? The area trapped between these guys is given by this formula here. So as you know, I try not to kill us with memorization and things we have to memorize all the time. This is one thing you just have to memorize, unfortunately. So the formula is area equals 1/2 the integral starting at alpha, ending at beta, of the function of theta squared d theta. Now, don't forget the square. A lot of students will forget that square. You'll get a wrong answer. Also, don't forget the 1/2. A lot of students forget that and get a wrong answer. So if you remember, this formula is basically take your information, take your alpha, your beta, stick it in, do the integral, you get your answer. All right, now there are a couple of things to remember though. I'll leave these as a couple tips. First tip is this integral here rarely can be done by hand. I mean, maybe if you had to, maybe if somebody locked us in a room and said, you can't come out until you do this integral by hand, I probably could. But the algebra is probably going to be pretty nasty because, as you know, these r equal function of thetas typically have trig functions. So you're going to have sine squareds and cosine squareds and things like that, but those aren't integrable. Sure, you could do like some power reducing formula or something like that, but that's just a mess. So for many of these, we can just use a calculator to pop out this definite integral. And that is the good news. is that it is a definite integral. It goes from alpha to beta. It's not an indefinite integral. All right, a couple more tips. You might have to find the alpha and the beta yourself. They will not always provide you with the starting and the ending points. You say, well, Devin, don't they have to? Like, how else would you know? Well, they'll phrase the problems, possibly like this. If they say, find the area of one petal of this polar curve right here, and that's all they say, well, then you're going to have to find the alpha where the petal starts, and then the beta where the petal ends. And so you have to think about that. Now let's think a little deeper about that. How would you find where a petal starts and a petal ends? Well, notice that's when the R is equal to 0. You're at home base, you're at the origin, and then it grows, and then at some point it's going to come back to 0. And so you can set your function of theta equal to 0 and solve it. And if these guys, as they do, typically have trig functions, you'll get multiple places where that function is 0. Okay, so that's something good to keep in mind here. All right. Now, so to find a bounded region, you may need to find alpha and beta yourself by setting f of theta equal to 0. All right, second tip, to get the area of all the petals, that's going to be a little tricky, because if you remember, part of this theorem here was that your function was non-negative. Well, we well know when you graph like a rose curve, some of these petals, for example, possibly this one, for example, is drawn when you have negative R values, because you're graphing, a certain window, some negative R values. Some petals are drawn in front of you, some petals are drawn behind you. And so this theorem here would not be applicable for things like this. But it's an easy fix, actually. Actually, this is quite a simple fix. What you can do is very simply find the area of one petal, right? Maybe one that has a positive R value. Here, let me sketch it right here. Maybe this guy right here. And then when you get that answer, just multiply it times 4, right? Or times 3, or times 5, or however many petals that you have. So that would be the trick to the second tip here. To get the area of all the petals, multiply the area times the number of petals. All right, now, we're not going to do an example in this video. We just wanted to set up the theory behind how you find the area of a polar region. In the upcoming video, we'll actually work a couple examples out.